It's 11 o'clock in Germany, in Europe, and many people want to come in and join our webinar today. So, dear participants, so good to have you here. And after a short intro presentation, I'm really happy to tell you that Dr. Srinath Rengarajan and Julia Schreier are waiting for you. They are in the background already and they are good to go. Now we have to start. Welcome to our webinar, Liquid Hydrogen Enabling Resilience and Scale, together with HEMTRON. First of all, hello from my side. I bring your hydrogen project where capital demand and decision makers meet. For that, also HEMTRON is partner from us because they want to recognize opportunities, open doors with me, take responsibility and accelerate success together. It's so good to have you here and please let's join the next 1.5 hours. We have the tailored consulting, so our expertise is your success if you want that. We have the basic, we have the starter, and we have the advanced package, basic reach, or tailored consulting. What you need, you can get. Our great partners and customers, you can see them here in the overview. The Smart TE will take place in June in Munich. Efficientix, Electrolyzer Fuel Cell Forum in July in Lucerne. EKPO Fuel Cell Technologies. Extreme H World Cup Racing Series with fuel cells. GP Joule, Hans Esser and partner HEMTRON, like we are here today. Hyvolution Paris, H2 the magazine, the shipping company Leis, Senko Capital, Smart Test Solutions, cell voltage monitoring, the Stadtwerke Stuttgart, so our regional energy supplier, Toyota Germany and Water Stuff and Sun, Week of Hydrogen, Wirt Leasing, and perhaps you in short. There you go. You can sign up for the weekly newsletter and then get the latest webinar dates direct into your inbox. And finally, and then I'm ready to go, we love Q&A. Dear participants, use the Q&A button, write us your questions, and Julia and Srinath will answer the questions or try to. So we read every answer. We read it and every question, sorry, and then we will see if they can answer it. So very welcome, Julia and Srinath. You are in the background, and while you are coming in, we have a poll for our participants. Hi, Julia. Hello, Srinath. Good to have you here, because we would like to activate you right now, dear participants, and we have the question: how would you rate your knowledge in the liquid hydrogen value chain? So it's now your turn. Please give us your answers. How would you rate your knowledge in the liquid hydrogen value chain? Very good, good, low, or very low? We'll give you some 20 minutes, and in the meantime, I understood, Julia, you're ready, and Srinath, you're also ready, and we could go into the introduction. Who is HEMTRON? So happy to have you here, and welcome.
Thank you very much, Silke. And thank you for you all to join the meeting today. My name is Julia. I'm responsible for the hydrogen midstream part, meaning I here. I am combining the hydrogen production and the customer with like efficient supply chain solution. I am in contact with several technology partners for that and also production partners. And in HEMTRON, I was actually the first employee, so I was shaping the idea of HEMTRON together with my team and turn it from the very first steps into now our business plans. I have almost 5 years experience in hydrogen infrastructure now, and in my former company, for example, I already integrated hydrogen infrastructure into a business unit. And also my background is industrial engineering, where I already put very much focus on hydrogen. For example, I wrote my bachelor thesis about fuel cell materials and my master thesis about hydrogen infrastructure. And I am very happy to discuss with you today about our topic.
I'll take over directly from Julia. Very happy to be here, and thanks for having us, Silke and the Hydrogen Moves team. And I'm very glad that over 100 people are taking time to listen to us on this very interesting topic, and to also hear our perspectives and share their questions and perspectives later on in the Q&A. A little bit about myself. I'm the director for downstream and business development at HEMTRON. I bring over 10 years of experience in strategy and leadership roles from the global automotive industry. So I don't originally come from the hydrogen business itself, unlike some of you, the participants here, who maybe have 20, 30 years of experience in the industry. But what I do bring to the table is an understanding of strategy and execution, especially coming from a customer perspective. And that's what I will share later in the webinar today. In my earlier company, I was involved with the ideation of the HEMTRON company, and coming from the shareholder side into my current role. I had in earlier jobs with the global automotive industry, as well as now at HEMTRON, focus on more commercials, partnerships, ecosystem building, growing business and corporate growth. And for that, I draw on, apart from my experiences, my educational background in strategy and in automotive engineering. I think you've heard a few times from me and Julia about HEMTRON, also from Silke talking about this company. I would like to share maybe 20, 30 seconds while the rest of you are still answering the survey, who is HEMTRON? HEMTRON is not a very old company. It's a 3-year-old startup in the meantime, with our headquarters in Hamburg. We are a subsidiary of the Oil Invest Group, who own and operate one of the largest refineries in northern Germany, and also have over 2,000 refueling stations spread across Europe, so coming from the retail business side. But HEMTRON as a business unit, as a subsidiary, is focused on building a hydrogen value chain, not in terms of owning and operating a lot of assets, but rather in terms of orchestrating different market participants and creating this market, so as a market maker. And in this space, we focused ourselves strategically a lot more on the topic of liquid hydrogen, and primarily with a focus on the European market. But don't worry about it if you're not from Europe in the call today. Our discussions are more on a global level and on a technology perspective and adoption perspective. So the takeaways from the webinar you can, of course, also carry forward and use for your businesses in other parts of the world as well. And of course, who knows, maybe there are opportunities for us to partner and collaborate on building this business globally in the future. Yeah. Without spending too much more time on what the company does, and rather jumping into the topic of discussion today, maybe first we have a quick summary of what the results are from the poll, and then we'll take it from there. Yeah.
So yes, we do have, and not all have answered, but I think it's a good picture. I am now closing the poll, or tell intermediate results here. If you want to click, you can do that right now. Answer in the poll: how would you rate your knowledge in the liquid hydrogen value chain? At the moment, it seems, Julia and Srinath, good to have you here, because just 16% say very good, 32% good, 44% low, and 9% very low. So in German, we would say da ist Luft nach oben. So there's a lot of potential to bring the fantastic facts that you have sampled in the last months and years, what I know, to the people. Thank you.
That's good to know, and it's a typical normal distribution curve, right? So at least for the people who are already experts with very good knowledge and good knowledge on the topic, bear with us if some of the content is a bit of a repetition or easy for you, because there is I think over 50% of participants who are at least in their own beliefs quite new to the topic. So we will try our best to match the knowledge levels of everyone and take everyone on board. And for doing that, you can see already what is the agenda that we have in front of us. I will start a little bit with where we are today in the hydrogen industry, and specifically as far as the European market is concerned. And in our experience, feel free to have a different view on that. In our experience, what are the main challenges that you have seen in the industry in the last 4 or 5 years? Yeah. Followed by that, I would invite my colleague Julia to give a techno-economic perspective focusing on liquid hydrogen. After which I would gladly share my own experiences of downstream and business development in the last years in this topic, providing a more market and application perspective on where and how liquid hydrogen, in our belief, will make a lot of sense in the coming years. So let's get started. Where are we today in the European market? There is a lot of news that you see around hydrogen. A lot of it was also bad news sometimes, but that's understandable. It's a nascent industry. It's an industry that's just coming out of its baby shoes, and it's growing. There's a lot of also positive news around how the industry is expected to grow, coming mainly from the topic of how do we achieve climate transition in many different sectors. And just looking at the numbers, in terms of electrolyzer capacity, there's over 2 gigawatt that's already under construction in Europe. The expectation is within the next 25 years, we would have over 73 million tons of hydrogen that's required from a demand perspective. But if you look at it from today's perspective, it's probably around a fraction of that, right? In terms of how that is in a global context, the expectation from those companies that you see in the source below is that roughly a third of the hydrogen demand globally would be coming just from the European continent. China is, of course, also a very major player and building up a lot of scale, as it is in many other different sectors. Same applies also to the hydrogen sector. In terms of project announcements, not the construction that I mentioned earlier, but in terms of announcements, in fact, Europe actually leads in terms of hydrogen-related projects with over 600 globally. That might change in the next couple of years if we are not fast enough in execution, because there are other countries who are also having a lot of appetite. One of them I already mentioned. But there's also a lot of commitment backing up those projects with over 175 billion euros, which have been announced to help some of those projects. Some of those projects are also a part of the IPCEI, umbrella coming from the European Union. And a lot of the recent impetus, especially in the last few months, has been coming also because of the geopolitical situations that we are currently finding ourselves in. But we'll come back to that when we talk about applications. If there is so much momentum and so many great projects being announced and so many electrolyzers being built in the continent, it's a great industry, right? It's amazing. But is that true? Actually, no. We also have a lot of challenges that we are looking at or that we are noticing when we talk to people in the industry, when we talk to hydrogen producers, when we talk to hydrogen off-takers. And a lot of that comes down to the fact that this is a value chain, a supply chain, which needs to be built from scratch. And a lot of projects that are being announced or that are already being constructed, especially, are very limited in terms of how many tons of hydrogen they can produce, or in terms of what kind of geographic scale they're able to address, especially in Europe. And this means that they lack some sort of scale economies. There are exceptions. Some projects benefit from incentives and so on, but that is not a sustainable strategy in the long run. At some point, we need to think beyond incentives. I don't want to talk too much about the politics around incentives, but the fact is that we need to go more into execution and we need to think bigger. But why are the projects that are announced so far typically much smaller? Because one, the technology needs to be proved, and two, there is a supply and demand mismatch. The places where it's easier to produce hydrogen are not necessarily the places where you need the molecules. And the different industries, the different segments which expect that they will want hydrogen in the future as a part of their decarbonization journeys are not yet willing to make the investments or don't yet need the hydrogen today to sign big offtake commitments with producers, which will allow the producers to do a FID or investment decision on the assets that they need to buy and install and scale up in order to bring down the costs. And a big part of that is also the midstream component, which my colleague will talk about in a few minutes, which is the I don't want to say the art, but rather the science of how much molecules we can move from the point of production to the point of delivery and how we manage this entire midstream part of the value chain. Yeah? And the consequence of all of these fragmentation and smaller scales and economies is that there are a lot of projects which are announced but not completed. So 600 projects that we saw on the previous slide, hardly a fraction of them are having FID, and an even smaller fraction of them are close to being completed and delivering hydrogen. So there is a need to synchronize that entire value chain so that we are able to bring all those different participants in one line and have a yellow brick path that they're following towards their destination. And there is, if you think about what kind of solutions are needed, we need to be smart and flexible and cost effective in terms of how we move those molecules, addressing directly the topic of transport and storage bottlenecks. We need this end-to-end thinking so that we are connecting the supply and the demand with that midstream component. So not just thinking about where we are producing and what kind of offtake we have in the vicinity of that production location, but rather how we think of it in terms of a more a bigger picture perspective. And then if you're thinking about a bigger picture, it's very important to think about who are those customers, because you cannot build a project only depending on, in most cases, you cannot build it only depending on one customer or one industry or one factory as your potential off-taker, right? And how can we focus on tackling those bottlenecks and bridging across those silos? Let's look at it from a techno-economic perspective, and I invite Julia, please, to take over from me and provide you her expertise on that topic in the next minutes.
Thank you, Srinath. So I'll give you some more insights now on the supply chain perspective of liquid hydrogen. And let's start right into it. So I think we all agree, and Srinath also introduced that the midstream part is one very important piece of the puzzle in the hydrogen value chain. But today there are still a lot of challenges. So many green hydrogen projects, they deliver their hydrogen in gaseous form with trailer transport, but it has limited capacity and with around 1 ton. And this limits also the distance of delivery. So you have a maximum delivery distance of 200 or let's say 500 kilometers. And this is restricting your customer potential, and also restricting the overall market to grow and making a tradable product out of it. Even though it works for now and it works in small ecosystem, we need some more concepts to grow the market. And that is one of those ideas is the pipeline. So many hope that the pipeline will solve all midstream problems. But the pipeline, once maybe installed, will not be connected to everyone in the first minute. And also politics decides about it. That means you are very dependent on political decision on other infrastructure provider. And a third very important issue with the pipeline is actually when you use the hydrogen for mobility application, you don't know yet what purity the hydrogen has in the pipeline. And that is very critical for fuel cells, because if there's just a little bit impurity, you have major damage in your fuel cell. So There is a third option which is often discussed, which is the long-term overseas transport via ships. And I mean, this is very well and optimized in terms of transport. So when you only look into transport, this is a very efficient solution. But also here, the first and last mile must be integrated. And you are again very dependent on external players like politics, like ports, like technology to be ready for it. And also this concept can only be initiated once big volumes are needed. And that sets very high entrance barrier to the market. So in summary, I mean, there are a lot of good concepts already existing, but there is a solution needed that is not an isolated optimization, but that combines the needs of also upstream partners or production partners and the downstream partners together, and that efficiently connect everything along the overall value chain. And we believe that liquid hydrogen could be one of the solutions to solve those issues. Before we start into the liquid hydrogen value chain details, here are some liquid hydrogen properties, so we know what we're talking about. It has very, very low boiling temperature, the second lowest after helium. And that is, of course, critical for the material selection. The density is quite nice with 70 kilograms per cubic meter. But here I need to say that in real storage, you always have a little bit less because liquid is not in a stable state, and you always have a gas phase as well, which of course has higher density, so lower density. And that means in total, you have a little bit less of those 71 kilograms in your real storage. A very nice side effect of liquid that it is of very high purity, and that is because every other molecule than maybe only helium is solid at that temperature, and that means the liquid itself is very pure, and you don't need to clean the hydrogen before, for example, fueling it into fuel cell cars. Also, we have a very nice energy density that exceeds the density of the the gaseous hydrogen options. Liquid hydrogen is not a new idea. Liquefaction plants exist for over 60 years now, and the market has reached a value of $45 billion. The daily capacity is around 600 tons per day, most of it in the US. And the major technology providers are only 3, and those are quite dominating the market today. And on the right side, you see our status today in Europe. So while the US has a lot of liquid experience already, in the US, there are only around 30 ton per day production capacity, even though there is already some announcement for growth. And we believe that this market has even much more potential. And that is because if you have a liquefier, then you connect your hydrogen production project to the global market. Because you're independent of local infrastructure, you can connect even remote regions where you have maybe high renewable potential to this hydrogen market, and you are very independent of external factors. And at the same time, you can reach a lot bigger customer base, which can initiate the market making. Let's have a look into the liquefaction process. I don't want to go too deep into it, but hydrogen liquefaction is not as simple as, for example, air liquefaction. That is not only because of the cold temperature, but also because of the negative Joule-Thomson effect. Hydrogen has until a temperature of minus 50 degrees roughly. And that is why the overall process is a little bit more complex. You see the process on the left upper side. So you have gaseous hydrogen as input. And in a first stage, you pre-cool it with liquid nitrogen to around minus 150 degrees. Then you have a cryogenic adsorber to remove impurities, which can damage your turbine in the next stage. And in this next stage is the actual cold box where you liquefy the hydrogen. Here you cool down the hydrogen with another medium flow like hydrogen or helium or another mixed refrigerant flow. And you in a last step, you expand the hydrogen in a turbine. So in the end, you have liquid hydrogen at minus 253 degrees. It is important to mention that you also need a auto-para conversion in that process, because otherwise you don't have a stable fluid. The equilibrium of auto-para in liquid is different to the equilibrium in the gaseous phase. That's why you need to take care about the transition of auto into para hydrogen, and that is done with catalysts. So this overall process takes around 3 kilowatt hours per kilogram in like mid-size liquefiers. The costs are around 3 million per ton per day capacity for mid-size equipment. And the nice thing about liquefaction is that they have, or liquefiers, is that they have a very long lifetime, more than 20 years. Some are in operation for over 40 years because they're very like stable systems. On the lower left side, you see a potential project site on which shows like from the hydrogen production to the liquid hydrogen transport, how such a location can look like. In blue framed or dark blue framed, in the middle, you see the actual electrolyzer of 300 megawatt. In the orange frame, you can see the gaseous storage. That is because you need constant supply of your liquefaction, which cannot just be turned off when there is no hydrogen available. It has a minimum part load of 30% roughly. So you need to have a continuous flow of hydrogen into it. Yeah, and on the upper left side, you see the actual liquefaction unit, which is not so much equipment and rather simple. You just have compressor, a pre-cooling box, and a cold box in summary. And on the lower left side, you see how liquid hydrogen can then be transported in a logistic or refilled and so on in a logistic area. This whole project needs to be optimized in terms of process, because you cannot just look into how to produce your hydrogen best or how to liquefy best. We need to consider all parameters and optimize the overall process. And that's what we do in our own software, which we have developed. That means considering all energy market details, all technology limits, and all regulatory facts, and taking all that into account, we can optimize SUH and optimizing the plant configuration. How is actually transported the molecule of liquid hydrogen? So it can be transported via trailer. This is already happening today. Also via ship. As you might have heard in the news, there are already some ships delivering liquid hydrogen, and some are now in development, and you can transport liquid hydrogen via container. And this should be our focus for today, because if you have a standard transport container, like a 40-foot container, you don't need additional infrastructure. You don't need external factors. You just integrate a container in existing infrastructure modes. For example, trucking, train, shipping, and you can operate it from today on. And because you have those single units of transport, you increase your resilience because you don't depend on just one transport medium. And that lowers your transport risk. You have flexible supply of different units. And also because you reduce your handling step. You just fill it once into the container and then you bring this box to the end customer. You also reduce a lot the complexity in transport. And that is how you can integrate hydrogen actually as a commodity in the market without waiting for someone else to make their decisions first and without major changes in infrastructure. So actually, this is something that you can integrate today in the market, or you can start this transport from now on. On the right side, you see how a container looks like. So it is like a standardized cryogenic container. It has around 3 tons capacity, and actual standard is around 30 days no boil off. It depends a little bit on your filling level, of course. And there's also containers available that have up to 200 days no boil off. Then you have a liquid nitrogen shield around it. But there is no active cooling of those containers. And I mean, they're existing today, and this is a product that is available on the market. On the lower left side, you see exemplary PNID, just to have a little bit of an idea how such a container looks like. You have an outer shell, then you have a vacuum with a multi-layer insulation. And then you have the inner shell or the inner tank where the actual liquid is. And of course, a lot of piping and some valves that can release boil off once you need to release the pressure. Because that is essential, the pressure build up, you can see on the lower right side, is very critical. So once you have reached the critical time, you see an almost vertical curve, and the pressure is rising very quickly, and this can be very dangerous. So you need to be careful about your venting and your maximum transport time, because this vertical like graph is because you have a little bit of space left in your container for the gaseous phase, and once this is kind of full, you have a very sudden increase in pressure because the gas phase is really correlating with the rising temperature. So it is increasing very quickly. So liquid hydrogen has also a big advantage when it comes to the application in mobility. And that's why I would like to give you some insight into the refueling station. And liquid hydrogen is not only of advantage when you want to refuel actual liquid into the tank, like for example, Daimler trucks, but also because the refueling station setup is much more simple than a gaseous hydrogen supplied station. And on the upper side, you can see that the gaseous supply, or the gaseous HRS, has a lot of different components. Like first, you may need to purify it, to compress it. You have the different pressure storages. You need to cool it down before dispensing it into the vehicle. And that means higher footprint, lots of energy consumption, and also your back-to-back is limited because once your pressure storage is empty, you need to wait until the compressor can refill them again. On the other hand side, the so-called multi-purpose station, which is on basis of a cryopump, you have liquid hydrogen as input, and this cryopump system can pump the liquid into high pressure gas or into SLH2, which serves then the liquid trucks. And not only having those two different fueling techniques, you also have a very simple equipment. You just have the cryo pump, which is a very powerful pump. You don't have any back-to-back problems. The footprint is much smaller and the energy consumption is much lesser because, like I said, the cryo pump is very efficient. You can use the cryogenic energy of the liquid for the refueling process. And of course, it is cold. You don't lack cold. And that's why you can refuel very fast the vehicles. You don't need to care about overheating the tank. So let's have a look into the cost perspective. So here you see a comparison of LCOH for mobility application. On the upper part, you see the local production methods, which has a distance of around 500 kilometers from production to fuel station. And on the lower side, you have overseas transport example with also usage in mobility. And here you can see that in the gaseous container transport, and we always assume the same production cost, you have very high logistic cost because of the lower capacity of your gaseous trailer. And also the dispensing costs are rather high, and that is what I mentioned before in the last slide. The refueling components are just more and more expensive, especially when it comes to volume. When we compare the pipeline transport to it, we have, of course, a very low pipeline fee. But like, as I said in the beginning, you don't know how much you need to purify. So this black box can be even higher because we don't know yet how much we need to purify the hydrogen out of the pipeline. And this can be a very complex process. And then again, you have the same dispensing cost, roughly, maybe a little bit higher because especially for last mile pipeline, you have a rather low pressure coming to your hydrogen station. And now comparing the container transport to the gaseous concept. We have higher upstream cost, of course, because we need to take into consideration the liquefaction cost, which has quite an impact here. But therefore, you have very efficient transport cost, and also the dispensing costs are rather low, especially again when it comes to higher volume. You always have some boil off. This is something that is going to be optimized. There's a lot of optimizing potential, and this boil off factor can be reduced in future. We can also have a look into the overseas transport, so comparing ammonia shipping to liquid shipping. And the important thing here is that, of course, ammonia transport via ship is very cheap, but then, of course, you need to crack it. And the last mile is the same as almost here. So the last mile from the point of from the harbor to the end customer must be done if there is no pipeline, for example, with the gaseous container transport, and that is making this whole concept more expensive. While in the container transport concept, we don't have those many handling steps again. You have just a huge midstream part where you transport your containers, but you don't have so many extra steps you need to take into consideration. And that makes it very efficient in the overall supply chain. So in summary, of course, for every customer situation, for every value chain, it can look different for sure. And sometimes another option is much better than this. But in general, it is important to have this holistic view on the supply chain. We need to consider every step along the supply chain from upstream to downstream and not just isolated optimize the different sectors. And so, as you can see here, liquid hydrogen is not only a good option in a qualitative sense because you have much less independencies and more flexibility, but also in a commercial way, it can make a lot of sense. And now I'm handing over to Srinath. There is also the downstream topic where liquid hydrogen can play a major role.
Thank you so much, Julia. And I think the participants were now treated to a very technical perspective on what's the components in the liquid value chain and how it adds up from a cost perspective, especially when you take the example of mobility as one potential end customer segment. Bear in mind, these are indicative costs. I just want to say one thing about that before we go into the next slide. These are indicative costs based on an LCOH calculation with various assumptions in terms of how far the hydrogen is transported, how much the volume of hydrogen is, which is produced at the electrolyzer in terms of scale and what kind of costs come out of it, etc., etc. But just to give the participants a perspective on how those costs add up, especially when we are talking about growing the business and not only doing local for local, small, regional or localized supply demand ecosystems. But before I talk a bit more about that, I want to provide first a market perspective, an application perspective. And I mentioned at the beginning, there are a lot of different demand sectors that are looking to incorporate hydrogen in as a part of their clean energy transition journey. Yeah? And let's look at some of those examples without going into too much of detail. What you see on the table here is different offtake segments and what kind of volumes of hydrogen they expect that they will need. An analysis or a first evaluation of how this demand is distributed, especially geographically, but also in terms of what kind of purity of hydrogen they need in terms of class of hydrogen for those sectors and in what time horizon they need and whether they need it in gaseous or liquid form. In almost all cases, in the end, inside the fuel cell, for example, the hydrogen is probably going to be in a gaseous state when it's being used. But here we're talking more in terms of in what form it's needed before that, or kind of stored on board in a vehicle, for example. Yeah. And the last column is the willingness to pay. Again, a qualitative evaluation based on dozens, if not hundreds, of discussions with various industries over the last 3 or 4 years that we have had, as well as what you've heard in various conferences, events, etc., from sector experts about how much they can afford to pay per kilogram of hydrogen. Yeah. And since we talked a little bit, and I saw also in the chat there were some comments about the trucks. Let's start maybe with that. First of all, under heavy-duty trucks, there are different technology concepts. Some of them are based on 350 bar gaseous today or 700 bar gaseous in the coming couple of years, as well as this is one special truck from one company which is looking exclusively at the subcooled liquid concept. Generally, it's a time period of 3 to 5 years before they are talking about series production of these vehicles. There are some pilot vehicles and small series, etc., already coming to the market before that. But for fuel cells, generally, they need a higher purity level. And in terms of where this demand is needed, it is moderately distributed. You can imagine that it's along the highways where the trucks are plying or at hubs, especially when it's coming to regional distribution kind of use cases. But each truck has anywhere between 40 to 80 kilogram tanks on it. So you add up the amount of hydrogen per truck into the number of kilometers that a typical truck drives in Europe, especially for a fuel cell truck. I'm not talking about city distribution, which is probably more of a battery electric application that focusing on the hydrogen trucks. The offtake volume is quite significant. So it's a very important offtake sector for hydrogen mobility. You compare that with city buses probably as a different use case. They are mainly gaseous technology based. The willingness to pay is similar, but the time horizon is smaller because there's already trucks with fuel cells buses with city buses with fuel cells operating today in some cities and some municipalities. But the demand location is a bit more concentrated. Generally, they are refueling at the depots. You're not sitting in the bus when the bus is going into a fueling station and tanking petrol or diesel today, right? It's similar. But in terms of volume, it's a bit more moderate in compared to the trucks. In terms of light vehicles, a typical fuel cell-based car has anywhere between 5 to 8 kilograms of gaseous hydrogen on board. Some OEMs have already announced series production in the next 1 or 2 years. The willingness to pay is typically higher for such vehicles for the fuel. But the challenge is this is a highly distributed network. For a single city, you are talking about at least 10 or close to 10 fueling points that are needed. But each point doesn't need the same kind of hydrogen requirement that a heavy-duty truck has, for example, because a large-scale truck HRS catering to a heavy-duty truck would probably be at least 2 tons dispensing capacity per day, whereas for one of those stations, one of those 10 stations in the city, you're probably talking about a couple of 100 kilograms a day at best in the first years. Maybe in the future it's a bit more. Yeah. Compare that with a different case of mobility like aviation and flights. This is much further out. There are prototypes today, but there is nobody talking about series, I wouldn't say production, but application of liquid hydrogen-based aircrafts in the 2030s or mid-2030s. It's probably even later, but very high purity requirements, very high offtake volume. To give you an example, a small to mid-sized airport in Europe expects by 2050 to have anywhere between 50 to 60,000 tons of hydrogen demand per year for the aircrafts that they operate. But it's very concentrated because you're only delivering to the airports, right? There is no mid-flight refueling when you're talking about passenger flights, commercial flights, right? There are other applications like research institutes, which have much lower volume demand, but the willingness to pay is much higher. There are advanced manufacturing industries which are similar, but have a different time horizon in which they need a little more hydrogen requirement that they are expecting. And then you have some industries like chemicals or steel, or especially a lot of process industries where the demand is concentrated. So you're delivering to specific factories, very, very high demand requirements of hydrogen, maybe even within the next couple of months, if not the next couple of years in some of those cases. But the challenge is here, you're not talking about high purity hydrogen, you're talking about probably hydrogen which is being burned for process heat, for example, where the requirements in terms of purity are comparatively lower. And there is a correlation with the willingness to pay as well, because you see that when the purity of hydrogen that's required is not very high, then those are also industries which are not very willing to pay 8 to 10 kilograms or 10 euros or more for a kilogram of hydrogen. They're probably looking more at a 3 to 5 euro per kilogram price band in the midterm, right? If you look at all of that across these are just some sample industry segments, but if we are to think about what are the takeaways that we have by looking at just that sample of industry segments, there are 3 takeaways. Julia, if you could just click once. Mm-hmm. The first thing is that different industries have different needs in terms of how much hydrogen they need, yes, for sure, in terms of offtake, but also in terms of where they need it, what kind of purity they need, when they need it, is it in a gaseous or liquid form that the hydrogen is stored on site or on the vehicle, and how much they are willing to pay for it. Yeah? The result of that is that there's a huge market fragmentation that hydrogen developers, project developers, infrastructure companies have to reckon with in terms of how the value chain is set up. So it's really a mosaic of industries in the offtake side. You can't depend on one single industry to build a huge plant, because there's a time horizon about when the series production starts or when it's scaled up to much higher volumes. And this becomes a challenge for the suppliers, because they want to take FIDs and build much bigger plants today so that they can bring down the costs that the industry customers are willing to pay. But they're not able to reach this FID because there is no synergy on the downstream side or the ability to build up sort of off-stake ecosystems or concentration of demand, which can lead to scaling that up. Now, I'm conscious that I'm making a couple of statements here, and let me put them in a bit more context on the following slide. If you're looking upstream, especially when you're talking about suppliers, on one hand, we have sort of the small to mid-size, let's say, local projects that are already being built. Some of them are operating very successfully. Some of them are very special projects which have benefits of how they manage their energy or how they manage land or other resources, which enable them to be competitive. But in general, if you're talking about the landscape of the projects in Europe that we have in right now, most of them are 10 megawatt or smaller projects. The good thing is, and there are advantages to every one of these use cases, the good thing is they are much closer to what their local demand centers are. They are smaller projects, so that's easier to do an FID. They don't need the huge offtake volume commitments. They're faster to deploy as a result. But on the other hand, scalability of those projects is difficult. Once you have that electrolyzer in place, it's not easy to just scale it up to 100 or 500 megawatt or something. And the supply of hydrogen from these projects is then typically limited to the gaseous form, which means that there is probably a 300 to a maximum 500 kilometer radius to which they can supply. And beyond that, the economics don't add up anymore. And we heard about where liquid hydrogen scores a lot of points on the midstream and logistics side. And that brings me to the next kind of upstream projects, which my colleague also mentioned earlier. This is the case of overseas transports, with, for example, Central Europe or Western Europe being the demand center, but the production of hydrogen happening in locations where there is much more advantageous factor costs, input costs, like the Middle East, like North Africa, like parts of Spain, or Nordic countries where there is a much higher amount of sun or a much higher amount of wind energy that can be harvested at a much bigger scale, resulting in much lower energy costs. I mean, you're talking about a couple of cents per kilowatt hour of energy cost for the electrolyzer as well as for the liquefier, if you're building a liquefier there on site in one of these locations, which brings down the purchasing cost of hydrogen or production cost of hydrogen rather significantly. But then the challenge comes, how are you transporting those molecules from those much more remote locations to where your demand centers are? For example, along the highways in the Autobahn in Germany, or in France. So larger volumes means better scale, better cost on the upstream side, but then you have the challenge on the midstream side of transporting and bringing it to the downstream locations. And here, of course, we have different possibilities. Like the liquid hydrogen topic that we are talking about, but also possibly other derivatives. Ammonia is one that's being actively pursued for some industries like fertilizer that could make a lot of sense, or other carriers like LOHCs, etc. There are, of course, some challenges with such an approach. There is an infrastructure dependency. You need to build up bunkers and terminals at ports. You need to have reconversion facilities. If you're talking about ammonia, for example, you need to crack it at the point where you receive it before you can ship it as gaseous form, or then add a liquefier and make a liquid out of it, which again adds costs on top. And as we are seeing, especially in the last few months, if not the last couple of years, from a European perspective, there's a lot of geopolitical risk that also needs to be factored in when we are talking about importing a lot of energy from outside, be it the situation in Ukraine or in the Middle East with the Strait of Hormuz. I think a lot of you are aware of these challenges. And that brings me to the part at the middle, which is where we are talking about larger projects, but mostly domestically within Europe. So making use of offshore wind, for example, or other possibilities like that. I mentioned some of them earlier. But here you're talking about regional projects, but which are still, relatively large scale and centralized. So, regional hubs and so on, which can then be combined either with a pipeline or with a liquid-based transport chain to bring the molecules to the demand centers. Now, the advantage is you're putting these projects in, again, locations with lower production cost economics, And input factors, for example, in Norway or in Spain or in Scotland, which brings your domestic cost down, production cost down. Additionally, it's a European or within a Euro project, which means that there is a system resilience component that comes in, and you're able to build sort of base load through industry clusters around those projects, or by combining those projects through the gaseous as well as the liquid supply chains. On the other hand, of course, you have to remember that if you're building a project in Europe, it's a high capex project. For doing an FID, you need a long-term offtake contract, and we just saw on the previous slide that a lot of industries are hesitant to commit today to what they will need in 3 or 5 years. They don't even know if how much they will need at that point of time. And like I mentioned earlier, this is production to demand mismatch then makes it even more reliant on the efficiency and costs in the midstream logistic solution. Yeah? Just to provide a perspective on what's happening upstream. And the main point is we need all of this. It's not an either or. It's not that we just need overseas import and therefore we don't need any local production. Yeah? At the end of the day, depending on those different customers that you saw on the previous slide, different value chain combinations will result in different LCOH, and something or some option, some configuration of the value chain could be more favorable for one location, one type of customer, and not be the most ideal for a different location for a different customer or a different industry. Okay, that's important to keep in mind. Now, if you have to take all of this together, all the different things you've been hearing from the two of us for almost an hour now, there are some main advantages on the downstream side, which result especially from a liquid hydrogen value chain. There are 5 that I want to highlight. The first one is, and this is almost summarizing a lot of things that we have talked about in the last few slides. So I don't want to spend too much time on every example, but the first one is that there are demand ecosystems that you're able to build by bundling offtake across industry segments. With a standard container solution, you're able to modularize and make it flexible how you transport those molecules, and doing that allows you to send the molecules over a longer distance to more different demand centers, and that helps you to bundle the offtake a little bit across industry segments. Yeah. Think about the example of the multi-purpose refueling station that my colleague talked about. It's the same refueling station which can cater to vehicles which need 350 bar or 700 bar or liquid or cryocompressed even, and that means that different vehicles can take the hydrogen from the same refueling station, and thereby the demand of that refueling station or the offtake of the refueling station is a bit higher. Yeah? The second topic is, or the second advantage potentially is, that with those container solutions, basically, I touched on this already, you have a high volume last mile delivery opportunity that's quite efficient, right? Think about the example with aviation that I talked about. One of the airports that I spoke to told me very clearly that they expect, at least for the first 20 years, that they're going to be relying on road or rail-based container solutions, because even if they have a pipeline, they don't have the space in the airport to build a purifier and a liquefier, etc., right? Maybe in the future they are able to build a bigger bunkering solution, and we have mastered the boil-off element to such an extent that we don't lose hydrogen every time we move it from one container to the next, but that's not there yet, right? So these kind of solutions, again, make a lot of sense. Thirdly, we shift the complexity upstream. So if you think about the process layout that my colleague shared, the fact that the liquefaction is done upstream at a place where there's lower energy, renewable energy available at a lower cost, means that the end use location at the customer doesn't need extra infrastructure. Like I mentioned just now with the liquefier at the airport, or a purification unit, or a cracker for the ammonia, or pipeline connectivity and related fees, or huge storage spaces for gaseous hydrogen. And all of this complexity is moved upstream, and that makes the customer's job or enables the customers to go about their jobs in a simpler way. Yeah. The fourth advantage is that element of energy security and resilience that I spoke about, where you're not depending on overseas import, at the same time not sacrificing the scale, which is the fifth advantage as well, which is that you're able to produce more hydrogen at a lower cost, because you're able to send it to more efficiently to different segments, to different demand ecosystem centers, etc. And all of that adds up. So there's a sort of a reinforcing circle of puzzle pieces that come together at over a certain demand threshold. We cannot do that only if we talk about local ecosystems with small demand. But when we're talking about how we grow the industry, then we believe from all of these perspectives that we shared, that liquid hydrogen has its own important role to play. There are some other advantages that the more technology proficient aficionados of the industry would understand and appreciate, like using the cold or rather the lack of heat of hydrogen in thermal management processes. It could be data centers, food processing, etc. kind of applications where that is an additional advantage. But here I'm talking only about those main advantages that we see crystallizing out of all these techno-economic and process perspective of liquid hydrogen combining with the customer perspective. That brings me to our last slide that we want to share with you. What are the main three takeaways that we would like to share? The first one is scaling. Using those containers as a standard modularized flexible solution, in our view, enables scaling the market. The second one, also not to be to be underestimated, is the question of resilience of the domestic energy market. And I said earlier that it's not either or. It's not that you can rely purely on import or purely on small projects. You need a complete mosaic of different kinds of projects, of different configurations of the value chain, and some of them also need to be European projects so that the European energy resilience is or system resilience is also built up in the process. And finally, I mean, I talked more from the downstream perspective, and I showed you how different the demands are in different segments. Using those synergies that we have in place or we can build into the midstream and upstream parts of the value chain while we are configuring those value chains means that we'll also be able to bundle offtake across sectors and unlock demand in the end across sectors, and maybe in the best case scenario also convince some of those industries that I talked about to shift forward their time frames, not wait for 3 or 5 or 10 years before they switch to hydrogen-based energy solutions as a part of their operations, but also maybe in the next 2 or 3 or 4 years. And that would be a win for all of us. With that, I conclude my part of the presentation, or our part from the HEMTRON side. Please feel free to get in touch afterwards if there are questions as well. I think it makes a lot of sense that we have Silke back with us now and do more the questions that have come from the audience during the webinar.
So big round of virtual applause to Julia and Srinath. We had also in parallel a lively discussion in the chat, by the way. So good to have you all in. It seems that we have really interested participants today, despite it's Friday. And I can tell you, Julia and Srinath, not to take more minutes, we can directly go into the Q&A because we had a lot of questions. So just let me see. Here, I have to scroll down. Okay, are you ready?
Sure.
Sure, good. Then let's directly start with Lutz Schilling. What is the price of green liquid hydrogen per kilogram at a public refueling station today and in 2030?
Do you want to address that, Julia?
Yeah. So when you look into German hydrogen refueling stations, there is actually a nice map online where you can see actual pricing, and this is around 70 euro per kilogram. So that is what you pay on most of the refueling stations today. We have recently been in Switzerland, and here you pay around 20 francs, which is quite high. And of course, sometimes you find very low price refueling station with around 11 euros, but in general, most of them are around 70 euros at pump. And this is actually far away from TCO parity when it comes to trucking. And because TCO parity you would reach with around 8 euros, let's say. Yeah, so there's a lot of potential or a lot of need for improvement.
If I can add to that, because there's a 2030 element, or maybe even an element looking further into the future, there is the Global Hydrogen Mobility Alliance, where we are also a part of, where we had very intensive discussions with many people in the value chain about what the vision should be. And there is even a target or a vision or a desirability to go below 8 euros to closer to 6 euros per kilogram for some applications, especially also in the mobility side. And well, the good news for those of you who are looking at that number and wondering, is this crazy? Is actually it's achievable, but the achievement of that requires configuring the whole value chain and not just working only on the downstream or only on the upstream side. Yeah. So you need to think about it in a big picture perspective, and you need to think about how you configure the entire value chain. And then across the value chain, what kind of technology and commercial levers are available, not just economies of scale, but also from a technology perspective on every step to bring down cost, to optimize it. And that's a very, very big discussion that we can have around that.
Okay, Felix Haberl, next one. What is your perception of the technology readiness level, TRL, technology readiness level of the midstream technology for intercontinental LH2 shipping?
So, I mean, when it comes to container transport, containers are available on the market. So it's a ready technology. There's no need for development, even though I think you can still improve like cost down or improve boil off. There is, of course, some regulation issue. It's not quite sure on how you are allowed to transport it now because no one took care of those questions so far. So this is more a regulatory aspect. And when it comes to bunker shipping, I mean, there is a ship existing that is shipping liquid hydrogen from Australia to Japan. So again, here we have existing technology that can be improved.
All right. Enrique Troncoso, can you elaborate a bit about the auto-para conversion in the liquefaction process and how this affects the LH2 plant outputs?
Sure. So in gaseous form, you have a higher share of auto hydrogen, so around 75%, and only low share of para hydrogen. And this shifts when it comes to liquid hydrogen. You have actually 99% para hydrogen in the equilibrium. And if you don't take care of this transition during your liquefaction process, then this transition will happen later on when you store it, and that transition is an exothermic process. That means you release a lot of energy, and this will cause boil off in your tank, and that is very critical. So in the end, you don't have your liquid anymore. You lost all your energy you put in, and this is done in the liquefaction plant with like catalysts. And this requires actually a lot of heat or this energy, because it also in the process releases a lot of heat, which must be cooled down again. So without this conversion, you can save a few kilowatt hours per kilogram of hydrogen actually, but it doesn't reduce the output of hydrogen in the end because you convert it.
All right, Elena Vyazmina, do you foresee any limitations to the liquid hydrogen supply chain resulting from Seveso 3 requirements?
Well, we need to see. So our focus is right now the container transport, and we try to optimize that. We will see what comes from experience from their project as well. So I haven't heard any special requests for now.
Okay, and again, Elena, are any changes in regulations needed, for instance, ADR?
Let's say it like this: you can transport containers on road today with existing ADR regulation, but it is a little bit restrictive because it says how much you are allowed to fill your liquid container and how much safety buffer you need and so on. So yes, you are able to drive around your container already under existing regulation, but it would be nice if there's also some progress on it and some adaptation. When we also get better in technology, also regulation should adapt to the technology and allows, for example, larger volumes to be transported.
All right. Sotiris Papadelos, does the ambient temperature affect the storage time of liquid hydrogen?
Definitely. So when you store your container directly into the desert in the sun, of course, you have higher heat input in your container, and this will reduce your holding time of the container because you have just a lot more heat transfer into the liquid. So the 30 days are for like not under standard European conditions now, not extreme.
Isan Rani, please provide your recommendations for options of large-scale storage of liquid hydrogen rather than tanks.
No tanks. Difficult to store liquid hydrogen than without a tank. So you can store it in the container itself. So having many containers, so which you can flexible transport to different hubs, but it's also kind of a storage. And a second option is, of course, that it is stored in the ship itself for a while, but you always need some, if you want to store larger volumes, you have those spherical tanks. You might seen them when it comes to the rockets. These are quite large spherical tanks, very low boil off, almost neglectable, and that is the best solution for now.
There you go. And Rajesh Kumtikar, energy for liquefaction is shown about 10 kilowatt hours per kilogram. Are efforts on to further optimize in order to make more attractive options?
Indeed, yes. So there are two options of improvement. So one is improving the existing process, meaning you change a little bit the parametrics of your process. This is done by in deep technical R&D. But there's also another option, which is an actual project today, and that is the magnetothermic cooling, which means you cool down with magnets. And that is very interesting, actually, because this significantly can reduce the energy consumption. So down to maybe even 6 kilowatt hours per kilogram. But this is in really early stage. They are still in, I don't know, to be honest, the TLR of this project. But this is not a commercial project yet.
Okay. Then we do have one of our lively discussions from the chat, Sirisha. Without liquid LN2 as a cooling shield, can't we maintain the no boil off condition? What do you particularly mean by a subcooled liquid hydrogen flow, high flow, madam?
Mm-hmm. So maybe I start with the second question. So subcooled liquid hydrogen is pressurized liquid at 16 bar filled into especially Daimler trucks, that they have designed that refueling technology. And because it's a liquid, which is pumped directly into the vehicle, you can easily pump it. It's a liquid, right? So you can achieve high flows. You don't have troubles with gas management or anything. So the actual pump today on the market can go up to 1,200 kilograms per hour, even more. So there is a lot of potential when it comes to liquid refueling, subcooled liquid, so under pressure refueling. And this subcooled is actually the case because when you have higher pressure, you have a higher boiling temperature, and that means you have a rather stable fluid and it doesn't boil off as quickly. And the first question about the liquid nitrogen shield, I mean, no boil off is, at some point you always have some heat which is coming into your container. So there, after some time, there is always some evaporation happening inside the container. Even though you have a liquid nitrogen shield, this will evaporate as well. And at some point you have a like warmer nitrogen, which introduces the heat from outside then into the liquid hydrogen tank, and then you always have some evaporation happening. But I would say 200 days are already quite a lot, so you can name it already no boil off, but to be very strict on here, there is boil off happening. Yes, that's not a no boil off system.
Okay, so next one, Dirk Fischer. Hi, Dirk. Great to see you here. A comparison would be appreciated. Liquid hydrogen moisture content versus compressed hydrogen moisture content during transport, dispensing into the vehicle tank system. Any idea ratio?
Well, there is no moisture in liquid hydrogen because it would be ice, right? So the liquid itself has no moisture because when it comes to minus 253 degrees, it's 100% solid ice. And this will then, the ice will fall down and it is very unlikely to be transported, or especially also in liquefaction process, it is absorbed in the purifiers in the liquefier itself. So actually there is no moisture in liquid. And so the comparison is almost, I mean, there's always, risk. There can always be some particle moved into a tank, whatever, or some solid particle in the liquid somehow. But yeah, you can say it's almost zero, while in the gaseous form, you always have a rather high risk of moisture in your gas. And this depends also on your process.
Okay, Roland Ademi. As I saw in the slide of LCOH, boil-off accounts for about €1 per kilogram during liquid hydrogen container transport. How long does transport take? Is the boil-off hydrogen lost and vented? Couldn't we use it, for example, to cool the tank through the wall to minimize heat flux, or reliquefy with a JT valve and return it to the tank? So first question, he has got two.
So a container claims to have 30 days no boil off, which means no venting. That means, of course, there's some evaporation happening inside the container. You have a little bit of gaseous phase inside the container, but it is not vented up to 30 days. And in our LCOH, we assume that our delivery time in short at least in the shorter transport, we don't reach those 30 days because this would be a really long-term transport. That means we have no losses actually during transport. The losses are happening when it comes to the refueling station, because then you have some heat coming from the ambient temperature again, because your pump is not always used, and then it warms up just a little, and then you have a little bit of boil off coming out. Also, your pump doesn't have 100% efficiency. It always have some heat generation of the pump itself, and that causes a little bit of boil off again. So that's where the actual boil off is happening, at the refueling station, and not actually when it comes to transport. And so far the gas, so when you transport more than 30 days and you have to vent, this is just released. So right now there is no project when it comes to reintroduce it into the tank, also because right now the 30 days are enough. I think there are still some possibilities which can be figured out, how to enlarge the no boil off time. And maybe could be Joule Thomson valve. I think could be an interesting idea to figure out. But for example, there are some cooling systems on the market that are adapted to the refueling station and that cool down again the liquid, so it doesn't have so much boil off when it comes to refueling. But this is just adds up a lot of complexity. So we hope that through this efficient transport within 30 days, plus improving the refueling technology, there can be done quite a lot already without investing in so much additional technology.
Okay, and the second question from Roland, when do you estimate that it will enter service in the aviation industry, 2040 or later?
I think that's a question more for my part. We hope it's earlier, let's be honest, but there are a lot of market conditions that will dictate when it actually happens, right? For how long have you had fuel cell cars and fuel cell based other vehicles as prototypes already? And yet we are not in a position where they are in series production today, right? Ultimately, it'll come down to when companies like Airbus are willing to make that a serious part of their portfolio. But for this, they need the infrastructure to also play along. And there we have this classic chicken egg situation. And that's where topics like bundling demand and bundling offtake comes in, because together, by putting together the whole value chain and working together, you're able to accelerate instead of just waiting for someone sometime to do something and make it realistic.
And perhaps, Srina, to add here, really fresh from the Hannover Messe, what I heard about, let's say, so please correct me, but for the licensing in aviation, for the products that you then bring in new, it's, with much cost on the one side, and also takes some time, and it's really, umfangreich, really,
right.
Many things to sample here, right? Is that correct?
Right, absolutely. So the prototypes already exist today. They're flying around. You have good companies, great products for using liquid hydrogen based tanks and flights which are out there. But the operationalization at scale needs a lot of moving parts to come together, and that will take time from a technology as well as from a value chain perspective.
Yeah. And those who have the experience in licensing and other processes here protect their IP. So it's a way to go, for sure, to work together. Yeah. Okay, so looking to the clock, 7 minutes to go. Some 2-3 questions left, so I think we're really perfect in timing. Miriam Theis is the next one. You're not yet a producer. don't own assets, have no experience on transport. The numbers are from public sources. How can you prove these numbers can become reality?
I know it's a question on the numbers, the LCOH for Julia, but I would rather take this question, and I would like to remind the colleague first. One, this is a free webinar, and at the very beginning we said we're going to share information which is for everyone, open to discussion, and not proprietary information about what we do. Two, we did not have any slides where we said what is HEMTRON doing and where we have assets or projects or partners, etc. So please, we need to carve that out. That is not a part of today's discussion. That's not the focus today, right? But coming back to the question itself, putting those disclaimers out, these are not public source numbers, all right? There are a couple of oligopolies in the market who are maintaining high prices and in whose interest it is to not incentivize the growth of the market. This is clear to all the customers that we speak to. We can, of course, rely on their numbers and say, yeah, the container costs 800,000 euros today or 1 million euros today, and you can forget it. You're never going to scale the business with that kind of cost. And the people who are sitting on those technologies have not done enough to bring down those costs. So we can talk about those numbers. And of course, when we say these company costs are possible, or this is how we see the LCOH, we have data behind that. We have ways of reducing the cost that we have looked at, that we believe in, and that's how we come to those numbers. Otherwise, we can just put a crystal ball out there and talk about this without having any proper databases or just some research institute studies to discuss this. So can we prove this is reality? Yeah, we can, but that's a separate discussion and not for today.
And Miriam, I think also with your company, there was a lot of exchange between HEMTRON and you. So it's always good to work together here. And the next question comes from Chen Kao. Among the many proposed applications, which one do you realistically expect to translate into actual liquid hydrogen demand at scale? Where in the liquid hydrogen supply chain do you see the biggest remaining technical gaps? Do you see liquefaction as the key limiting step? And if so, what advances do you consider realistic in the near to mid-term? Based on engineering experience rather than concepts, which interface or subsystem represents the highest risk in real projects today?
Realistically, at scale, today is not there, right? If it was, then we would have many more liquefaction plants, many more market participants in Europe in this business. But you look across the pond and you have much bigger liquefiers which are already operating since 50, 60 years in the meantime in specific applications, right? But looking forward, we believe that definitely mobility is one of the lead markets, given the amount of hydrogen that's required and the kind of value chain configuration that's required to deliver it on the downstream side. Aviation, purely based on the amount of hydrogen that the airport needs, for example, that I talked about earlier, is of course a very key market. And then there are, of course, some other markets which are maybe not the biggest in terms of volume, but which are very exacting in terms of requirements, in terms of purity, etc., which also will need that kind of a value chain to cater to them, right? Did that answer the question? There's also something on technical gaps, I guess.
Yeah, I can answer
Yeah.
that one. So technical gaps in so right now we can build up with existing technology the supply chain as I presented it. But of course there is a lot of potential for growth. And one of these are for example the containers. They are quite expensive for now, and we already took some considerations and we elaborated some costs down via scaling and what is needed to do that. And there is a lot of potential still when it comes to the cost of container. Technology is already quite good when it comes to container. There is some R&D needed when it comes to interfaces, for example, from container to refueling station. Also the cryopump, there is one now from Bosch. Everyone knows that, I think, or that is very present right now in the news. But also there are not many market players who actually offer refueling station as a system. So the overall concept, not just the pump. And there is still more like research needed to actually have a very efficient dispensing process, not only a efficient pump, but process. And in liquefaction, I mean, this is what I mentioned. We need to come down with the energy consumption, and people are working on that already. But so far, the energy consumption, at least in large scale, is already good enough that we are quite competitive when it comes to liquefaction. So in summary, I would say cost down for container would be important, and the interfaces are important. And in the end, the refueling station system, including the pump and the dispensing process, this is also a factor that needs to be improved.
Okay, so it's 12:30 here in Germany, but Aki for sure. Aki, hi, Aki Terumaruta. Good to have you here. Aki, we will bring your last question as a last question. Aki from Japan has got a question regarding the cryopump. I heard there are still many technical problems on cryopumps. What is your perspective on the commercialization of cryopump?
Yeah. I already mentioned that it's still critical, and we have heard a lot of horror stories about a lot of boil-off suppliers that promised much better than they actually did, and the number of suppliers are also quite limited. But this is actually changing now. So a few big players are stepping into the game now. They are now today improving their technology. And also, some say the Bosch pump made a very important step towards a reliable technology. And this pump is, for example, now in testing in Oakland in California. We hope to soon see some good numbers. I already heard some good news, but let's see how it proves itself now in operation. So far, until maybe 1 or 2 years ago, it was really hard to find reliable supplier for this technology. But because of some announcement from OEMs, people or technology provider also want to have a good product on the market. And that's why it is changing now towards a better product.
Okay, so thank you guys. Perfectly done. What a timing. Fantastic. We had a lot of people in. So it was overall, I would say 150 or something like that. Thank you very much again, HEMTRON team, Julia Schreier and Dr. Srinath Rengarajan. So cool that you joined us today. And I think we keep the process and keep the line here. And finally, I would like to give you the stage to say thank you, Julia and Srinath, and I wish you all a very happy weekend. Stay tuned. The next webinars are coming, and I'm really looking forward to it here. Thank you.
Thank you also from my side. It was a pleasure.
Yeah, thank you for listening. Please contact us on email. We have shown our info address of HEMTRON. We will respond you, and we also, of course, share the presentation. So if there are some more questions, feel free to reach out. Also, maybe on LinkedIn, however you want to.
There we do. Thank you again, and bye-bye.
Thank you. Bye.